Now, if you are in Europe somewhere, so somewhere in the south, you have some forests around, and then you have some wind which is playing with the leaves, and you have this sound around you. When you get to the tundra, it's different. One thing that I really like about these places across the Arctic is there's less noise, but still it's full of life. Well, often people think about the Arctic like there's no vegetation, it's kind of bare, or it's just all the same, but it isn't. Tundra it's full of vegetation, different types of vegetation, and it's extremely diverse, and it's changing from 1 meter to the next. On the one hand, it's kind of remote, yeah, and calm, but you're not really that alone. It's a very special environment.
Hi, I'm Stephanie Tomapos, and you're listening to Down to Earth, the show where we talk to incredible geoscientists about their science and its impacts on our planet. When I think about climate change, one of the first images that comes to mind is of a polar bear stuck in a giant chunk of ice and floating off to sea. While it's certainly a moving image, we have a whole lot more to worry about when it comes to a melting Arctic. Landslides, fires, 1.5 trillion metric tons of carbon released into the atmosphere, these are just the tip of the proverbial iceberg. So today, get your snow goggles on because we're taking a 1 kilometer by 1 kilometer resolution look at permafrost thaw and what this entails for us and our planet. Support for Down to Earth comes from the Inspire, Develop, Empower, Advance, or IDEA Committee of the IEEE Geoscience and Remote Sensing Society. The IDEA Committee is about empowering engineers and scientists to follow a career in geoscience and remote sensing. One way they do this is through their Women Mentoring Women program. This year-long mentorship program fosters careers and friendships across generations, disciplines, and geographies. To learn more, visit grss-ieee.org and select IDEA from the community header menu.
Permafrost is one of the what we call essential climate variables. The temperature in the ground reflects climate change. It's a kind of answer to what is happening in the atmosphere. We know the air temperature is increasing, steadily increasing, and that also determines what is happening in the soil.
This is Dr. Annett Bartsch. She's the founder and managing director of an Earth observation company called b.geos. Through this company, she uses satellite technology to study how permafrost thaw is changing our landscapes, contributing to climate change and impacting the almost 5 million people living in the Arctic's permafrost zone.
Now, thinking about like sea ice or glaciers, you immediately can see this from satellite. It's very easy to see. But permafrost, by definition, it's a subground phenomenon. And we cannot directly measure this. So people often wonder how you do this from satellite. How do you monitor something that you cannot see?
Permafrost is a tricky element to study because, as you just heard, it's not something that can easily be observed from space. But this is where Annett's work comes in. Through observing other elements like landform change, Annett can generate estimates on the distribution, magnitude, and impact of permafrost thaw. Let's take a listen. So correct me if I'm wrong, but my understanding is that we can't see permafrost thaw through satellite data. So how do you actually use remote sensing to study permafrost?
We really have to get an idea about what is happening to the temperatures in the ground. You can measure it by going to a certain place, make a borehole. Yeah, it costs something. And you need some infrastructure there to be able to do this. And then you can measure it in the ground. So that's one point. And there are a number of these points, these boreholes around the Arctic, where we have quite a good idea about what the temperature is. But it's such a tiny fraction of the Arctic that we can monitor with this. And we somehow need to fill these gaps. The international community, they define some specific parameters that should be measured. First of all, the temperature in the ground, at certain depths, but also this thickness of this thaw layer on top. Yeah, so which is actually by definition not permafrost because it's thawing in the ground. We refer to that as the active layer. And that's what we try to derive, the temperature and this thickness of the active layer.
And that's what you've been doing through the European Space Agency's Climate Change Initiative Permafrost project, right?
Yeah.
So, how do you measure the temperature and active layer thickness with remote sensing?
The surface temperature, this is something we can see from space. And that's what we try to integrate in the project. And we integrate that into models because that's the only way how we can get this information in the ground. We cannot go there, but we can model this. And then what we need to consider is the heat conductivity, so anything what is having the influence, how this temperature change at the surface is translated into the ground. That's the snow in the winter. Yeah, that we can also see from satellite. And that's then the type of soils. It's very limited what we can see regarding soils from the satellite, but we can see the vegetation. And vegetation somehow reflects what types of soil we find below. Yeah, and specifically in the Arctic, we have these gradients, dry and wet moisture gradients. It's a very heterogeneous landscape, and depending on whether you have it's wet or dry, you have different type of tundra vegetation. And that's we can see from space. So we can take this information and feed that to a model together with the land surface temperature and the snow, and then we get some subsurface temperature.
So it's a lot of mixing together different observed elements to create a better understanding of what we can't actually see, which is the permafrost layer. And you mentioned the different landscape plays a role in how you determine temperature too.
Yeah, this is also the main major challenge if we're thinking about using satellite data, looking at this, that it's so extremely diverse. And it's also changing. You have these seasonal changes, and then you can observe also these changes due to climate change, these long-term change, which overlap each other. And that's very much defining or the landscape, this presence of ice in the ground, or these changes of the ice in the ground, which shape the landscape. So it's not just flat. So you have what we call a microtopography.
I mean, I come from the Philippines, and there's a huge difference between my country, a tropical country, and the Arctic, especially in these areas, the tundra you're speaking. And I've seen changes back at home, but I've never seen these kind of changes in the Arctic. What do you mean by the changes? What exactly are you seeing?
One obvious thing, what is changing, it's land cover. So, and under land cover, what we understand here is the presence of lakes, the formation of lakes, the disappearance of lakes, patterns of flooding. And then we have what kind of counts in the category of hazards. We have lots of landslides in the Arctic, which are related to thawing ground. So landslide is maybe something that you are also familiar from your region. And there in your region, I think that's mostly triggered by the rain. Now in the Arctic, where we have permafrost, we have ice in the ground that thaws. So we also have a lot of water in the pores of the soil. The ground destabilizes this way and then the material moves. So that's what is triggering the landslides. So of course, at some point in the Arctic, this ice in the soil, it also comes down as rain. But the increase of the temperature and the melting of the ice in the pores, which is very crucial here in this case.
So there's one thing in common that we have, and another thing that I learned 2 years ago. Somehow I had this conversation with someone looking into satellite imagery in the Arctic, and he mentioned about forest fires, and I was so surprised that it happens in the Arctic. How do forest fires happen in one of the coldest places on the earth?
Yeah, one thing that often surprises people is that there actually is forest on permafrost. There are trees growing on permafrost. Yeah, so vegetation often depends on summer, July temperatures. There are areas with a really high temperature amplitude. So it's very cold in the winter, but it can be also rather warm in the summer. And there we also can have forest. And these forests because they can burn. So it's a very natural thing for a forest to burn. We have lightning, which can cause this, and we have drought periods in the Arctic, like in other places around the world. And parts of these forests are interesting for industry. So we have people there logging, and of course they are smoking, and then many of the fires are actually nowadays man-made. But then there are also what we call the tundra fires. So north of the tree line, you can also have fires. So what you need for a fire is you need some material that can burn. And of course, a forest, a piece of wood is something what can easily burn. But there are also, we have peat fires in the high north. So if it's really dry for a longer time and you have some lightning, this can be released. It's comparatively rare. You need really special conditions that it starts to burn. But once it burns, it's burning over a longer time period.
That's really surprising to me that fires happen in the Arctic. It almost seems unimaginable, but I guess I have taken us on a bit of a tangent. So I'd like to come back to your work on permafrost. With the project you have with the European Space Agency, you're using remote sensing to assess surface temperatures and plant moisture gradients. Then you're putting all this data into models that give you a sense of the subsurface temperature. And then what happens?
We try to go as far as possible back in time. What is, another problematic topic.
Okay, I definitely want to ask about that. But before I do, I want to know what you've been finding through this research. Anything surprising or exciting?
Surprising, maybe not. We have, regarding the temperature development, we already have quite a good idea from the boreholes. For all these boreholes across the Arctic, temperatures are increasing. And that's exactly the same story what we get from the satellite. We also looked at changes at the land surface. As you have the ice in the ground, and when this melts and the water flows away, then it forms depressions. We call this thermokarst. And that alters the landscape a lot. And we can measure the changes in the terrain, changes in the hydrology, all of these things happening related to thermokarst. With the satellite data, we can identify these areas, or we can actually quantify these changes. Like there are thousands of landslides, many, many more landslides than anywhere else in the world across the Arctic. And now with satellites, we are able to count them, and we are just starting to do this, especially with the new satellite missions and new techniques, machine learning and so on. We are able to do this, and now we can put numbers to this. And that's the exciting thing.
Up next, we talk about the challenges of assessing permafrost thaw over time. We also dig into how permafrost thaw is going to have a serious immediate impact on our way of life, particularly in Western countries. I bet you can't guess why. Finally, after all the doom and gloom is out of our systems, we share some hope for the future. All this right after the break.
When you were first in university, full of passion for science and tech, how many women were in your classes? And as you progressed, from undergrad to specialization to your first job and beyond, what happened? If you're like most scientists, technicians, engineers, and mathematicians, chances are the higher you climbed in your career, the fewer women you saw around you. But what if I told you you can help shift this trend? Research demonstrates that mentorship can have a huge impact on a woman's career. By choosing to mentor a young woman in science, you'll help them gain confidence, pursue exciting career opportunities, and even help increase their promotion and earning potential for years to come. Consider joining the Geoscience and Remote Sensing Society's Women Mentoring Women program and make a big difference in a young scientist's life. Learn more by visiting grss-ieee.org and select IDEA from the community header menu.
Welcome back. Today we're speaking to Dr. Annett Bartsch, founder and managing director of the Earth observation company, b.geos. Aside from a brief tangent into the fact that the Arctic has tundra fires, what? Can you believe it? Anyway, I digress. Now, We've primarily been covering Annett's work with the European Space Agency's Climate Change Initiative Permafrost project. This project is focused on developing permafrost maps derived from satellite measurements. Permafrost cannot be detected from space, but as Annett explained, there are many different surface features of permafrost terrains that can be seen from space. So Annett and her fellow permafrost scientists collect data on observable variables like land cover, land surface temperature, and snow water equivalent. They enter it into a permafrost model scheme, and from there, they're able to determine permafrost temperatures and thaw. And apparently, they're also able to take a look at these temperatures over time. So let's dive back in to find out how. Okay, so earlier when you mentioned studying permafrost thaw over time, you laughed. And I'm guessing it's because it's not easy to do. So, what's challenging about looking at permafrost thaw over time?
So thinking about these changes over time, we always have to think about changes over space. This Arctic landscape is extremely heterogeneous, and they are also changing over time. To identify this heterogeneity, all these patterns, really interesting patterns, specifically like polygonal nets and all these thermokarst phenomena, we are trying to capture the present state. Yeah, so that's what's technically possible. And then thinking about time, changes over time, we are not yet there. So all what we are doing right now is just some approximation. Now, when we model this temperature in the ground, the spatial detail that is used by 1 kilometer. So now think about what is all in this 1 kilometer. It's extremely heterogeneous. So now we have this one number per year over 20 years, this one number. So it's changing this temperature change or maybe the depth of this thaw layer on top. And then the question is this number, what does this actually mean at a certain place within this grid point, in this pixel? And how representative is it? What does it actually tell us? But that's what we can get right now. And if we are now looking at the entire Arctic, that already gives us some really valuable information on a regional scale. So we can at least say, okay, this region's temperatures are increasing faster than in another region. That's something that we can say of this. But the actual, what is really happening, we are really far away from that. There's still a lot to do in the future.
A bunch of questions actually pop up for me right now. I mean, what satellites are you using to gather this data? What challenges arise with satellites you're using? And if every pixel is more than a kilometer by kilometer, how do you deal with that, considering the landscape is so diverse?
Yeah, for research and specifically if you're looking over larger regions and changes over time, it is really important that the data is free. Sentinel missions are really important for research here because the data are available for free. Now, also, several of these sensors provide something quite novel. They have much higher spatial detail. That's exactly what we need. But they only started very recently, and we need to go back much further in time. So here we rely on other missions, past missions, thinking about land surface temperature. What's quite really useful here is the MODIS mission, due to the fact that it's existing for quite a long time, so for more than 20 years. So that's what we are relying on, these older missions. That's then a comparably coarse spatial resolution. So that's actually one of the main reasons why we are calculating this at the 1 by 1 kilometer. Still, we can use these new missions, which have a higher, give us a higher detail, like the Sentinel-1, the Sentinel-2, or these European missions, which give us a really nice account of, or some measurements across quite a range of the electromagnetic spectrum. So that's the visible, the near infrared, but also the microwave, the radar domain is reflected in Sentinel-1. This gives us some information that we can use to describe the current state and specifically the boundary conditions. The type of vegetation, and from that make assumptions about what are the soils, what then goes into the model. Yeah, so we have this land surface temperature changing over time coming from these older sensors. And then we can define the parameters of the land cover, land surface by using these comparably new sensors. And with this 10 meter, that's already fantastic. We are already getting somewhere. It's not perfect. Yeah. So we would actually need a much higher spatial resolution. But with the models as we have it now, we anyway have to come up with a parameterization of this 1 by 1 kilometer area. Yeah, well, we can still bring in some fraction of this and this type of soil here with this newer satellite data, but that's how we approach this at the moment.
It's really amazing to hear that a certain topic could involve a lot of kinds of data, from optical to radar to surface temperatures, and that's amazing to see that how harmonious these technologies can become if we know how to approach them and use them to the models. So, based on your findings from the ESA Permafrost project so far, what are the next steps? How can we use these findings to mitigate the impacts of climate change?
Yeah, so we can now actually pinpoint to areas where really things are changing. And that's quite important for the local community. So we can say, okay, this region it's warming faster than another one. And we can come up with a number or a year when we expect that permafrost goes. Yeah, so we can make some for the near future, some simple interpolations into the future, and then we can also validate or evaluate climate models, which can go decades, centuries into the future. And that's a really important application and something that we need to do now to work together with the climate modelers to help them to improve their models.
It will definitely be important to be able to model permafrost thaw well into the future because, if I remember correctly, there are a lot of people living in the permafrost region, right?
Yeah.
I think I read that there's almost 5 million people living in permafrost zones around the world. So that's a decent number of people.
Yeah. It's important for the people who live there, like to build roads, houses in these regions. But on the other hand, it's important for anyone else on the globe because when the ground thaws, we have an increase of microbial activities. We have a lot of carbon in the soil. And then this carbon goes as methane or CO2 into the atmosphere and contributes to the warming of the air temperature. So this is also an important point to consider here. So we have to make what we call the application or the use of what we are observing. So that's one next step. And the other, of course, you can always improve things. Yeah. So there are quite some things which are still unsolved, some uncertainties that we need to lower of our results. So that's also something that we have to consider. So we are not yet finished, really. So we produced something. It's a first version, and there's room for improvement.
Now, it obviously makes sense that permafrost thaw is a big deal for folks living in these zones. But for those of us living outside of permafrost zones, why should we care? How do we communicate the urgency to people?
Yeah. We don't know exactly how this will affect the climate in the future, how this will amplify the increasing temperatures. Yeah, and these increasing temperatures, it's a global phenomenon. Yeah, and this affects everyone. Or that's one of the things that we are trying to communicate to the people. So this is part of the story. And then something what has so far always been a kind of interesting way or interesting thing to communicate when you're talking to people in Central Europe was that all these gas resources or oil and gas resources that's built on permafrost in Russia. Alaska, we have the oil fields, and also in Canada, mining is happening in these regions. They really have to think about how things are constructed and how this, the construction itself, how it impacts the environment. They trigger thaw, and then also the other way around with the thawing ground, has an impact on the infrastructure in the Arctic, so on the people living there. And there are a lot of natural resources in the Arctic that play a role for people living elsewhere.
I think that's a really good reminder for people or a way to reach them, by reminding us that a lot of these resources people depend on in the West are extracted in permafrost zones. And especially with the price of oil right now, if we sustain damage to oil infrastructure because of permafrost thaw, those prices are only going to get worse. It feels really depressing to think about it, honestly. I mean, especially because changes are so slow and you're immersed in this work all the time. So I want to know what keeps you feeling hopeful.
Changes are slow, definitely. Yeah. And it's, if I think about all these local politicians here, they don't look very much far ahead. Yeah, that's a problem everywhere. Also, these local politicians or decision makers, they are embedded in this global framework. That's where things are happening, like on this a more international level. And there we saw a lot of things changing. We have now over many decades already this IPCC process, yeah, which is taking this information from scientists and trying to really pick out what is the important and trying to translate this to decision makers. So what we are publishing, what we are developing, that doesn't disappear somewhere in the famous drawer. It's picked up by these international organizations and it's communicated. They have people who are really experts in communication. So this is something what we lack as a scientist. So how do I communicate my results, my research, which is so specific, so narrow? How do I communicate it to the others, the non-scientists, to a decision maker, to a politician? And you need experts on this. And that's what we have nowadays. I find this quite encouraging.
Thanks so much for sharing that. I agree that more and more scientists are doing the work of translating their research for decision makers. Now, you seem really passionate about the Arctic, so I want to know what led you to open your own company and focus on Arctic research?
Well, I have a certain research interest, but I'm living in Central Europe. So if you're at a research institution and you say, oh, actually, my interest is in the Arctic, you're like, yeah, nice. Yeah, so if you bring in the funding, of course, you can do this. But actually, nobody is interested in what you're doing. There's no real research institution, specifically in Austria, which has a focus on the Arctic. There's in Germany, you have the Alfred Wegener Institute for Polar and Marine Research, but not in Austria. But there are companies, there's actually one more company in Innsbruck, which also has a focus on polar regions, more on the glaciers and on the ice sheets. So I saw that, okay, that this is a possibility, and I decided to do that. And now at my company, I can really focus on what I'm doing. Yeah, I'm doing the same like I was doing at the university. But some things are more complicated. I need to think about more management things. But on the other hand, my other things are much more easy. When you're female, of course, this is always a special topic in this kind of research environment and career development. And when you are in a bigger institution, university or some research institution, there is this very famous glass ceiling. Yeah. And one can spend a lot of energy on trying to get out of this glass ceiling, to really get into a position where you make the decisions. And after trying that for a long time, I just decided in a way to get outside of this house with the glass ceiling and build my own house, which doesn't have a glass ceiling.
I love that you decided to build your own house. I think that's a great approach to this glass ceiling problem. For other women geoscientists who want to pursue entrepreneurship or who are struggling to break that glass ceiling, what advice would you give them?
If you're a bit younger, things are nowadays a bit they're changing. I have the impression. Maybe it's not really the case, but I have the impression that you have much more opportunities now. You have these tenure track and universities try to have now more female candidates for these type of positions. So that's something was completely unavailable when I was at this earlier career stage. This option just didn't exist. So I think this is a really good thing maybe to try, but it always depends on what kind of research you do and what kind of setting you are working. So for me, I was lucky because what I'm doing is so much related to computer science. And there's really a potential for entrepreneurship. It was actually much easier for me than I expected. Once you start this process, you will discover that there is a lot of kind of institutions that can support you. At least that's in Austria, it's like this. And then also many universities that actually have this, they provide support in this direction. You just need to try. For me, it was really a wow effect. It was much easier than I expected.
So I guess you're saying that the system has already started to change in the community that you're in, and they have been more open to people, especially in the sciences, specifically women, to start something new. You just have to be bold and you have to try it out.
Yeah, that's exactly it. Yeah, you're phrasing that well. You just try. And if you don't try, then it won't happen. But you really have to make this step and try.
Well, that's all for this episode of Down to Earth. Want to learn more about Dr. Annett Bartsch research? You can find her on ResearchGate, and you can also follow along with her work through her company website at b.geos.at. Don't forget to follow us on Spotify and Apple Podcasts. And send some love to our sponsors at IEEE_GRSS on Twitter and Instagram, and IEEE Geoscience and Remote Sensing on Facebook and LinkedIn. This episode was produced by Nicole Bedford from Nicole Bedford Films, with help from me, Stephanie Tomampos. Graphics and design by Mylene Briggs of Killam Media. And a special thanks to Heather McNairn and Sean Kefauver for their support. I'm Stephanie Tomampos, and you've been listening to Down to Earth.